So then we move on to Rule 4. And Rule 4 answers the question, what one thing is crucial for life on Earth? I have a bunch of chemicals in front of me, and if you look at this, only one of them is really absolutely crucial to life on Earth, to the extent that we should look for it if we are looking for other planets that might hold life. And it's the one that I was just able to fill up out of my faucet for free, the water. This water is crucial for life. In fact, you can take it a step back and say that the liquid phase is what's really crucial. And Earth is special because we have a lot of oceans. We have a lot of liquid phase, and it's exposed to the energy of sunlight. So we can look around the solar system, we can look at all these different planets. And one of the ways that chemists can tell where things are liquid is we make a graph that has temperature on this axis and pressure on that axis. You see that this graph has solid, liquid, and gas phases. And so this line is the water line up there. And if you look at where Earth is right here. Earth is located between the gas phase on the top and the solid phase on the bottom, right in the middle of that Y. That means that Earth has a temperature and pressure that allows water to be liquid. That's really helpful and neat. Venus is too high. And Venus has too much. Any water on Venus would be steam. Any water on Mars would be either solid or steam because its pressure is too low. So temperature too high, pressure too low. Earth just right in the middle. Now there are some other things that you might notice. You might notice that Titan, the moon of Saturn, and it really is this orange color, is located in the middle of this Y right here. And this Y is the methane Y. So that means that Titan should have exposed methane oceans and rivers. And it does. We just saw them. But the problem with Titan is that it's too far away from the sun, and also methane doesn't have the same chemical qualities that water does. So I'm doubtful that we could have life there, but I'm going to say if there's one other place to look for life, it's probably Titan. So the ocean is really great for running chemical reactions. Liquids, you have them in flasks, right? And you mix stuff up and you make reactions happen. That's what all the chemists do in the movies. But the liquid actually has some hidden benefits. The liquid ocean actually keeps us cool by keeping us from turning into another Venus, by keeping a greenhouse effect from happening, by solidifying carbon dioxide. Now you know that the increasing levels of carbon dioxide, just to the level that it's been at, is worrisome. It was once much, much worse, and the Earth was in danger of boiling away all its oceans. But then a chemical reaction happened that happens in the liquid phase. Because CO2, water's H2O. If you take CO2 and H2O and add them together, you get CO3. You get carbonate right here. And carbonate in water will stick to calcium. And it will form a solid, calcium carbonate. The calcium carbonate will sink to the bottom of the ocean, and then the CO2 is no longer warming the air above. There's actually two other shields that are mentioned in the book, but again, this just a teaser. That's on page 100 or whatever. But the thing to know is when you look at carbonate mountains, like the Dolomites in Italy, a lot of that is old CO2 that's been trapped. And it's like the Venus atmosphere that could have happened is instead packed away into a solid on the bottom of the ocean until that was uplifted after a long time. It's much better to be in the mountain than to be in the air, especially with our current problems with CO2. If you take a map of looking for carbonate rocks around the world, they're shown in red here. Some of them are old, some of them are newer, but many of them date to this particular rule. We're actually going to have another rule that's going to make more carbonate rocks, and that's going to be Rule 9, which we'll get to in a couple of minutes. But this reaction that made the calcium sticking to carbonate, is actually very similar to explaining why the colors changed in this picture. Okay, you've probably seen this Van Gogh painting of his bedroom before, but you've probably seen it and you probably imagine it looking blue like this. It actually used to be purple. And you can actually trace that back to a particular chemical reaction that turned what he painted as purple into blue. And that chemical reaction is very nearly the same as the calcium carbonate one. It's just he used a lead pigment, a red lead pigment. It was cheap. He didn't have much money. Okay, so he put it on his canvas. Over time, the moisture in the air created carbonate from carbon dioxide. That reacted with the lead and made a solid. The thing is, lead carbonate is no longer red. Lead carbonate is white. In fact, this is how they used to make lead carbonate in a related process. If you want to make your own lead carbonate, it's actually pretty easy to do, and it's one of the older pigments that we have. You take strips of lead, you put them over old vinegar, and you have them in a shed with manure. Okay? Because you need the carbon dioxide. You need the other, and the warmth actually helps as well. Over time, a white crust will form on your strip of lead, and that is lead carbonate pigment. And then you can paint whatever you want from that. It's a really great opaque pigment. It's the same reaction that causes our oceans to be a chemical shield, just with a different metal. If you want to see a video that shows you the paintings of Van Gogh as they used to look, you can check out this link right here. And that just answers our question of the liquids are crucial to that process, and there are many other processes that they're crucial to in life. In fact, water changed the whole chemistry of the planet. It even resulted in what one author calls mineral evolution. You think of life as evolving, right? Well, because water was on the planet, the water allowed the minerals to evolve. It allowed new minerals. Earth is the most mineral-rich planet in our system because Earth has the most water. 4,000 kinds of minerals as opposed to like 1,000 or 2,000. So that's great, but there's a problem. Back before there was even life on Earth, there's a lot of oxygen. You know, it's pretty low on the periodic table. If you look here, it's right up here at number 8, so a lot of it's made in the stars. The problem is that oxygen is reactive. Oxygen reacted and made rocks and was buried, so it wasn't available for life. Now, our life definitely depends on oxygen. And so it's kind of hard to see, well, does this mean that the most important thing for life, the oxygen that we breathe, is gone before, and is life over before it starts? Okay? And that will bring us to Rule 5.